How do you know if you can attend every meeting on your schedule? Meeting rooms is a Pattern Mastery 100 favorite and a classic warm-up at Google, Amazon, and Meta for interval reasoning and sorting. Over 25% of candidates miss subtle overlaps or forget to handle back-to-back meetings. Master this.
Unlock a whole world of scheduling and interval-based interview questions. Let's break down meeting rooms using the basic approach, a reliable method for interval overlap problems. You're given an array of meeting time intervals where each interval is start, end. Determine if a person could attend all meetings. List of intervals, unsorted, each as start, end. Boolean, true if you can attend all meetings, false otherwise. Imagine planning your day with back-to-back meetings. Can you get to everyone without running late? Interviewers might ask, how would you quickly check if any two appointments on your calendar overlap? What's tricky? Input can be unordered. Meetings that end exactly when the next starts do not overlap. Only need to find one overlap to return false. First, sort all intervals by their start time. Then, walk through the sorted list. For each meeting, compare its start to the previous meeting's end. If the current meeting starts before the previous one ends, there's an overlap, return false. If you make it through without overlaps, return true. Let's clarify. Sorting is critical. Unsorted input can hide overlaps. Edge cases. One meeting, always true. Empty list, true. Edge cases. Empty list, true. Single meeting, true. Overlapping at end. 0, 30, 30, 40, no overlap. Sort intervals by start time. For each meeting from the second onward. If interval I0, less than interval I11, overlap, return false. Now let's solve solution 1, the min heap, or sorting, approach for checking meeting conflicts. Time complexity is O(n) log n, due to sorting the meeting intervals. The idea: first, sort all meetings by their start time. After they're sorted, walk through the list one by one. For each meeting, check if it starts before the previous one ends. If you ever see overlap, return false. If you finish the loop with no conflicts, return true. Even though this is called min heap, this solution uses sorting, but the logic follows the same principle. Track end times to detect overlaps. Line-by-line explanation of the code. We begin by defining a class called solution. This is just the wrapper that holds our method. We create a function that takes a list called intervals. Each interval is a meeting with a start and end time. Here we sort all the meetings by their start time. This makes it easy to compare each meeting with the one right before it. Think of it like arranging events in a calendar so you can scan them in order. We loop through each meeting starting from the second one. We do this because we are always comparing meeting I with meeting I1. This is the core check. We compare the start time of the current meeting with the end time of the previous meeting. If the current meeting starts before the last one ends, that means the two meetings overlap. If we detect overlap, we immediately return false, meaning you cannot attend all meetings. If we finish the loop with no overlaps, we return true. This means all meetings are spaced out enough and can be attended without conflict. And that's how this algorithm works. It first sorts all the meetings by start time, then checks one by one whether any meeting overlaps with the previous one. Efficient, simple, and elegant. Sorting the meetings costs O(n) log n. The scan afterward is O(n). Overlap happens when the current meeting's start time is less than the previous meeting's end time. No heap is required. The sorted list already gives us the correct order to detect conflicts. Now we test our can attend meetings function with a sample schedule. Input intervals are 0, 30, 5, 10, 15, 20. Each subarray shows a meeting start and end time. The algorithm sorts meetings by start time and checks for overlaps. If any meeting starts before the previous one ends, it returns false. Here, meeting 2 starts at 5, before meeting 1 ends at 30, so there's an overlap. Output is false, confirming the function works. The implementation efficiently detects overlaps and ensures the schedule is feasible. In this approach, we're using a simple brute force method. We check every possible pair of meetings to see if any two overlap. It's easy to understand and implement, but not the most efficient for large inputs. Time complexity is O(n) squared, where n is the number of meetings. Every meeting is compared with all others. Simple but can be slow if n is large. We define a class solution to hold our meeting schedule checking method. Define the function can attend meetings and get the total number of meetings. Use nested loops to compare every meeting with all later meetings. The outer loop picks one meeting, and the inner loop checks it against all following meetings. Check if the current pair of meetings overlap. If they do, immediately return false because you can't attend both. If all pairs are checked and no overlaps are found, return true, all meetings can be attended. This is a simple brute force method. Each meeting is compared with every other meeting, giving O(n)² complexity. It works well for small numbers of meetings but is inefficient for large inputs. Let's see how our solution checks meeting intervals and determines if all can be attended. Input intervals are 7, 10, 2, 4. Each pair shows a meeting start and end time. The algorithm compares each pair of meetings. If any meeting starts before the previous one ends, it overlaps and returns false. Here, 7, 10, and 2, 4 do not overlap, so the function returns true. Output is true, confirming the implementation works. The method efficiently checks for overlaps, handles all cases, and ensures accurate results. Let's wrap up the meeting rooms problem. It's one of those deceptively simple scheduling questions that interviewers love, and it quietly tests your logic around sorting and interval overlap. Miss a single detail, and you'll end up double booked. Breakdown recap. We're given a list of meeting intervals, each with a start and end time, and we need to determine if a person can attend all meetings without any overlaps. If any two meetings overlap, the answer is false, otherwise, true. Assess recap. The key insight here is that meetings can come in any order, and back-to-back meetings are allowed. So, we first sort all intervals by their start time. Then, we walk through the list, comparing each meeting's start to the previous meeting's end. If a meeting starts before the last one ends, we found an overlap and can immediately return false. If we reach the end with no conflicts, we return true. Structure recap. Our structure is simple. Sort the intervals by start time. Loop through each one, checking for overlap with the previous meeting. If none are found, return true. Edge cases like an empty list or a single meeting automatically return true since there's nothing to conflict with. Implement recap. We implemented the sorting and single pass check using built-in functions. Quick, clean, and efficient. When we ran it on LeetCode, the solution executed smoothly without any errors. Check recap. We tested multiple cases, including overlapping and non-overlapping intervals, and all returned the expected results. The time complexity was O(n) log n. For sorting, with only O(1) extra space. Closing insight. The big takeaway? Sorting is your best friend in interval problems. Once your data is ordered, detecting overlaps becomes a simple linear scan, turning what looks complex into something elegantly straightforward.